Myself, Rawat, Government College, Faridabad. Today we discuss prime number system. We have some abbreviation over here, that is capital N stands for natural numbers. For every natural number n there exists its successor number n plus 1 belongs to capital N. One is not the successor of any natural number, that is 0 doesn't belong to capital N. Principle of mathematical induction, that is, if Pn is a mathematical statement which is true for n is equal to 1 and Pn is true for n is equal to m plus 1, wherever it is true for n is equal to m, then Pn is true for all natural numbers. Okay, we have a theorem. Every natural number n greater than 1 has a prime factor. We prove this theorem as it is. We shall prove the theorem by lemma, by induction on n. For n is equal to 2, lemma is true for n is greater 2 is greater than 1. 2 has a prime divisor, or you can say 2 is the least prime. Suppose lemma is true for all natural number less than n. Now consider n. If n is prime, then the lemma is true because it has a prime divisor n itself. So assume n to be composite. Then n has a positive divisor n1, whereas 1 is less than n, 1 less than n, such that n is equal to n1 into n2, where 1 is less than n2 less than n. Since n1 is less than n, by induction hypothesis n1 has a prime divisor, say p, then p divides n1 and n1 divides n, therefore this implies p divides n. This proves the theorem. Okay, next theorem, that is called Euclid theorem. The number of primes are infinite. Okay, we have proof. If possible, suppose number of primes are finite. We prove this by contradiction. Let these be n1, n2, n3, and so on. Okay, p1, p2, p3, and pr. Consider capital N is equal to p1, p2, p3, p4, and so on, pr plus 1. Now n greater than 1, by above theorem n has a prime divisor, say p greater than 1, but only primes are p1, p2, p3, and so on, pr. So p is equal to pi for some I. Then p divides p1, p2, p3, p4, and so on, pr. Also p divides n implies p divides n minus p1 dot p2 dot p3 and so on, pr, or p divides 1, which is a contradiction. Hence number of primes are infinite. Not let p is equal to 2, 3, 5, 7, 11, 13, and so on be the set of all primes, and let s is equal to 3, 5, 7 be the set of all odd primes, then S can be divided into two mutually discount subsets having primes of the form 4n plus 1, 4n plus 3, and the set 5, 7, 11, 13, 13, 17, and so on can also be divided into two subsets having prime numbers of the form 6n plus 1 and 6n plus 5, where n is equal to 0, 1, 2, 3, and so on. Next theorem. The primes of the form 4n plus 1 are infinite in numbers. Okay, if possible, suppose primes of the form 4n plus 3 are finite, and let these be p1, p2, p3, and pr. Again consider n is equal to 4 p1 into p2 into p3 and so on pr minus 1. Then obviously n is greater than 1. So n can be written as the product of primes. Now n is odd. Obviously this n cannot be equal to, that is least prime. Then thus n can be written as product of odd primes. N can be written as a product of primes of the form 4n plus 1 and 4n plus 3. But if n were divisible by primes of the form 4n plus 1, then n would also be of form 4n plus 1, but n is of the form 4n plus 3. So n is divisible by at least one prime of the form 4n plus 3, say p. But only primes of the form 4n plus 3 are p1, comma p2, comma p3, and so on pr. Then p is equal to pi for some I. Now p divides n and p divides p1, p2, p3, and that implies p divides 4 into bracket p1, p2, p3, pr minus n. This implies p divides 1, which is a again contradiction. Hence, number of the primes of the form 4n plus 3 are infinite in number. Again, we have theorem of the form, the number of the prime of the form 6n plus 5 are infinite in numbers. If possible, let number of the primes of the form 6n plus 1 are finite and let these be p1, p2, p3, pr. Again, let n is equal to 6 into p1, p2, pr minus 1, then n greater than 1. So n can be written as a product of primes. N can be written as a product of primes of the form 6n plus 1 and 6n plus 5. If n were indivisible by primes of the form 6n plus 1 only, then n would be of the form 6n plus 1. So n is divisible by at least one of the prime of the form 6n plus 5, say p. But only primes of the form 6n plus are p1, p2, p3, and so on pr. So p is equal to pi for some I. Now p divides n and p divides p1, p2, p3, and so on pr. So p divides 6 into p1, p2, p3, and so on pr minus n. That implies p divides 1, which is again a contradiction. Hence, number of primes of the form 6n plus 5 are infinite in numbers. Not if GCD of a and b are 1, then every odd primes of factor of a square plus b square must be of form 4n plus 1. For example, GCD of 4 and 3 are 1. 4 square plus 3 square is 25 has an odd primes factor, say 5 of the form 4n plus 1. Similarly, we can prove another theorem, that is prime of the type 4n plus 1 are infinite in numbers. Possible, let p1, p2, and so on pr be the only of primes of the form type 4n plus 1. Consider n is equal to 2 p1, p2, p3, and so on pr bracket square plus 1. Now n is of the type a square plus b square, and GCD of p and b are a and b are 1. Also n is odd, so 2 cannot divide n, and all the prime factors of n are odd. So all the odd prime factors of the n must be of the form 4n plus 1. Let p divides n, then p will be of the form 4n plus 1, but the only primes of the form 4n plus 1 are p1, p2, p3, and so on pr. So p is equal to pi sub 4 some I. Then p divides n and p divides 2 p1, p2, p3, pr square, that is p divides 1, which is equal to, hence number of the form 4n plus 1 are infinite in numbers.